I'm here to introduce our newest project, InFrame++. It enables simultaneously screen human viewing and hidden screen camera communication. This work is done by the collaboration of 4 different institutes, and I'm everyone from Beihang University. Firstly, we can see that digital displays are all around our world. For example, currently we are all watching a digital display, and they are the primary information source in our life, and they content our eyes in many aspects. For example, we can browse their ads, watching movies, watching football games, and other things. To begin with the presentation, let's start with a scenario of our real need. Let's assume that we are currently watching this period of video. We always want to get some more related information. For example, where is this stadium, and what's the name of it, and how can I get there? We need both the video and some video-related opportunistic metadata. So there exist 3 kinds of solutions, as I know. First, we can directly show the scripts onto the video, but like this, it is it is very inconvenient and it blends with the video itself, so that it hurts our viewing experience. And the second solution is that we can embed a QR code onto the video. But however, it also hurts our viewing experience, and the information size is limited. The third one is that we can also temporarily quit the movie and open the search engine, search for the keyword, and get the information we want. And then we can continue to viewing the video. This kind of temporal compromise is also very complicated. Those solutions lead to certain inconvenience, and the problem arises: can we achieve both simultaneously? We want a full screen normal viewing, and meanwhile we want accompanying data communication, but they are imperceptible to our eyes. This is we see what we want to see, and our devices obtain what we want to obtain. So we propose InFrame++, which is a complete solution for this scenario. Let's first see video clips to introduce InFrame++. We can see we can choose an arbitrary video and type arbitrary text at here, and after clicking the apply button, we can see the video in the display, and our cameras can capture and decode the data. We have the demo yesterday, and I hope that some of you have already felt magic inside InFrame++. Yes, the text is intact. So that we want to realize this kind of dual mode communication. So the primary channel is screen to eye, and we want it to be guaranteed. And the second channel is screen to camera communication, and we want the throughput higher. So that the first goal is to keep intact viewing experience with no impairment. This is the challenges that how can we realize this, meanwhile embedding data without impairing. So the secondly, we want to have some good data performance as possible, and this is also a challenge. Is that how to boost the throughput and the reliability with moderate error rate. Note that the two seems contradictory with each other, so it is also a very serious problem. So how to deal with it? Let's focus on the first one first. Let's first see what one frame of InFrame++ look like. We can magnify it, and we can see exactly the embedded data inside it. And but we want it to be invisible. So I will then introduce how to make them invisible. We have found that there are perception gaps between human eyes and cameras. we have searched for many academic papers about human vision systems, and we have found that the human eyes is very limited. Firstly, the camera and the screen. Camera, as we know, is developing rapidly, both the resolution and the frame rate. And meanwhile, the human vision system is quite stable, and the mechanism can be treated as a low-pass filter. It is named flicker fusion by the neurologist, and if we see the flickers faster than 50 Hz, we can almost imperceptible to our eyes. So can we utilize this to realize our goals? Of course, the answer is yes. Given a pixel, we can add and minus certain brightness respectively to get complementary pixels. And multiple pixels form a pattern, and multiple patterns forms a frame. Those pairs of frames are complementary frames. We magnify a part of the frame, and we can see exactly the complementary patterns. This design is named Special Temporal Complementary Frames, STCF for short. And those pairs, side by side, are played sequentially encoded with an arbitrary video stream in a fast speed. When we play it at a high frame rate, the complementary frames are displayed on the screen, and our eyes are like a low-pass filter, which is what we see is the average of the pair. And our 15 people user study have proved this. As a result, our eyes see intact video when we watch those patterns, and meanwhile, our cameras take snapshots. This is difference of our eyes, and so that shutter speed can be set to a relatively small period, and so it can capture the intact patterns. And we want to dynamically encoding the data. So the data is time variant. When data changes temporarily, the phase may change, like this image, and like the typical low-pass filter, spectrum leakage will happen, which is exactly fake flickers in InFrame++. So how to deal with it? We apply the smoothing transitional frames. It is exactly used in the signal processing, and we adopt half-erased cosine waveform and to reduce these flickers. And our user study verifies this design. It really eliminates the possible flickers. So let's move to the second goal: how to fast and reliably encode and decode the embedded data. The main challenge is the interference from the video. We see that our scheme compared with the typical VLC schemes such as QR code, the information is not that clear. The brightness in the right image is very clear. The bits we can see is 1010. But the left image we can see only vague waveform, and it seems we cannot extract information from it. So in order to solve it, we borrowed the idea from the CDMA. It's called division multiple access. We divide each frame to multiple blocks, and each block is consisted of multiple cells. Every cell is a square of pixels. The encoding rule is simple. We first design multiple codes, orthogonal codes, to represent data, so that the cross-correlation result of different codes is almost zero, but that of the same code is a big positive number. And meanwhile, the background image and the code is not that similar, so that their cross-correlation is also near zero. As a result, we can cancel the noise from the background image. Moreover, we want some more additional rules for generating the CDMA codes. Firstly, the average must be equal to 0 because we want the frame to be complementary. For example, this code is invalid because the average is not 0. Secondly, the contiguous 1 and minus 1 cannot be too long. It will reduce the flickers. For example, this code is also invalid because the black line and the white line is too long, it's 4. Secondly, it must be unique subject to circular shift and unique subject to reverse operations. This is because that the capture, when we capture the display, it will face locating errors, so that these two pairs, each pair is also identical. Lastly, we design the code, and their maximum timing distance should be as high as possible, and the maximum is to the power of 2n minus 1. So as a result, in InFrame++, we designed these 4 codes for modulation, and their timing distance is exactly the maximum. For demodulation, it is similar to typical CDMA demodulation that calculates the cross correlation, and the difference is that we also calculate the cross correlation for certain offset within a given period, given range. And like this is the black border is what we locate. And for the calculating the cross correlation of different offset, we can see that the maximum offset, the maximum result is happened with a certain offset. It is exactly the correct location of the block. Lastly, we introduced several components for screen-to-camera links. Firstly, we introduced the locating method. We adopt QR code-like corner for localization, and the invisible alignment pattern for more accurate locating and rolling shutter detection. If rolling shutter happens, we can see that the border will be the contiguous frames of the border will mix together, and the border will be exactly hidden. So that when we do the cross correlation, we also calculate the variance of the cross correlation result. And if it is hidden, the result is very small. For example, in this image, the middle border is affected by rolling shutter, and it is detected. So we didn't decode data from there. For error resilience, we designed 3 methods named Mirror Guard, Channel Reference Blocks, and Error Detection and Coding. Due to time limit, please find the details in our paper. Our prototype consists of 3 parts. The sender is implemented in C# and HLSL, which utilize the GPU to help us do the blending work. We also implement 2 receivers. One is for offline, one is for online. The offline receiver is also written in C#, and the online receiver is written in C++ in Android platform. And our experimental settings we use gaming display named ASIL FG2421 which supports 120 frames per second frame rate, and 3 off-the-shelf smartphones for our cameras. We first designed various user study to do the subjective test to ensure invisibility. We invite 15 persons to participate in the study. The first chart shows that STCF is better than TCF, which removes the special complementary rule. And even when the amplitude reaches 40, the flicker is still invisible. And meanwhile, no artifacts can be seen because of the flicker fusion mechanism of our eyes. This chart shows that the cell size can be up to 7 by 7 when using STCF. and we choose 3 by 3 because it can support more flexible distance. It's as near as 60 centimeters. And from this figure, we can see that the transitional frames, when we set it to 4, it is enough for STCF, and the amplitude is set to 20. We also tested various video sources, and when the amplitude is 20, all of the video we cannot feel flickers, and we cannot feel flickers and artifacts. Next, we show the evaluation of the throughput and the bit error rate. The amplitude, we can see that the performance is not sensitive to different amplitudes. The error rate keeps under 5% when we set under this configuration. The second figure shows that using different coding parameters greatly affect the transmission speed and the error rate. And we finally choose the second parameter for the balance between throughput and bit error rate. The maximum throughput can be up to about 190 kilobits per second. It is rather high in invisible light communication. As expected, the farther distance, the lower throughput, and we found that our InFrame++ support up to 2 meters long, and we must say that the screen itself is only 24 inch. And we also tested using various video sources, and the throughput is quite stable. And the throughput is also all of the video sources support up to more than 150 kilobits per second. Finally, we measure the encoding and the decoding speed. The encoder can be real-time thanks to the GPU implementation, and the decoder's processing speed is slower, and is only about 3 to 4 frames per second. The latency is not too long for a relatively short message, as we show in the demo. To summarize, we propose a novel system that enables simultaneously screen-to-human weaving and hidden screen-to-camera communication. The techniques include special temporal complementary frames and smoothing transitional frames, CDMA-like modulation, robust block localization, and error resilience. Our evaluation results shows that we can achieve up to 190 kilobits per second throughput with moderate error rate. Okay, thank you very much. Any questions?